Welcome once again. It's Physical Sciences Extra. It's Saturday Extra. My name is Tinigo Kosa, and today we're going to talk about vertical projectile motion. Now, so the key words in our lesson today, vertical and its projectile. We have spoken about motion earlier on when we did some revision on grade 11 work. So you do have an idea of what motion is all about. We will, of course, be talking about equations of motion again, but specifically this time we'll be talking about vertical projectile motion. Now let's unpack this. What is this vertical projectile motion? Let's look at the focus of this lesson, and then we will be able to see where the lesson is going to take us. Now, we will be talking, or we will define, we'll explain what we mean by vertical projectile motion. We will also be looking at this concept here of the force of gravity. We will also be talking about acceleration due to gravity. Now, we have spoken about acceleration in the lesson I referred to earlier, but then we did not just speak of acceleration at that moment, including acceleration due to gravity. This one will be very specific. It's acceleration due to gravity, and we'll be talking more about it. We will know more about what this type of acceleration is. And we'll move on to talk about how can we represent this motion on graphs. You would remember that even in our revision of grade 11 work in terms of rectilinear motion, we also looked at graphs of motion. We will also have a chance to look at some of those in this lesson. And of course, like I said earlier on, we will also look at equations of motion as applied in vertical projectile motion. Now, let's define what this vertical projectile motion is all about. Now, projectile motion is an up or down motion. Now, an object should be moving either upwards or downwards. It's something that is actually moving in air, all right, if we're talking about something thrown within our vicinity on Earth. So we're looking at objects moving up and down. That's the type of motion we'll be looking at. And an object that is undergoing an up or down motion is called a projectile. Hence the name projectile motion. Okay? Because the object is moving on an up and down motion. That object, when it is in motion on an up and down direction, is called a projectile. Right. Now, we also know that if an object is moving, it is constantly changing its position. Now, for an up or down motion, how is that position changing? What do we call that type of positional change? The change in position of a projectile motion is along the vertical axis. And because it is along the vertical axis, the change in position is represented by delta y. Now, we will understand from the set of axes that we use to draw graphs that the y is the vertical axis, whilst the x is the horizontal axis. So we're using delta y because we're talking about the vertical displacement or the vertical change in the position of an object. Right. Now, when this motion happens, when the up and down motion happens, we know that for a motion to occur, there would be a force causing that motion. There will be a resultant force that is actually accountable for that particular motion of the object. Now, when an object is moving in an up or down motion, what force is at play there? Right, so what is gravitational force? Now, gravitational force, this is the force of attraction. The force of attraction between objects in the universe. Okay, so every object attracts another with some force in this universe. And this force, its size or its magnitude depends on two things. It depends on the mass of the objects, and also the distance between their centers. The distance between their centers. Okay? Now, when we looking at big objects like the Earth, the planets, the Earth, Mercury, or the Sun, things like that in the universe, you would see that we're talking about massive objects. But if we talk about small objects on Earth, for example, myself or any other object, a box lying on the surface of the Earth, there is an attraction between that box and the Earth, and that is the force of gravity. Now, you will agree with me that the mass of the box is so small that we may even think that its influence on the force of gravity is very, very minimal. So in that case, we can see that the force of gravity will depend mainly on the mass of the Earth. Hence, we usually say that the gravitational force is the force of attraction, or the force with which the Earth attracts the objects towards its center. Because the more massive an object is, the more force of attraction it will exert. So the Earth will be exerting much more bigger force of attraction on any object around the Earth. Okay, now the other question will be to say, how does this force of gravity depend on the mass of the object, and how does it depend on the distance between their centers? What has been established is that the relationship is such that the force, this force of gravity, the force is directly proportional. Okay, directly proportional to the product of the product, directly proportional to the product of the mass of the objects. And inversely proportional to the square of the distance between them. The square of the distance between their centers. Okay, so this is how the force of gravity depends on the mass and the distance between objects. Now, if we were to calculate for this force, the force of attraction between any two objects in the universe, this force, like we have explained there, we say it is directly proportional to the product of the masses of the objects. So if we're looking at two objects, say an object here and an object there, these objects will have mass, so it's mass for object 1, mass for object 2. And between their centers, there would be a distance. And that distance, let's call it r. Now, the force of gravity that exists between them, which is a force of attraction, is directly proportional to mass 1 times mass 2. Okay? And the same force is inversely proportional to the square of the distance between them. Now, when we put these two relationships together, we have a situation where on the left-hand side, we're still talking about the same force, so we'll write F. This will be proportional to M1 times M2 divided by R squared. That's when we put 1 and 2 together. Okay, now we have got a proportionality sign here, and to remove it, we need a constant, and the constant is G. This is the universal constant on gravity. It's called G. Now, when we put that down, then we can remove the proportionality sign, and what we'll end up with is a nice formula for calculating the size or the magnitude of the force of attraction between any two objects in the universe. And that will be equal to G, the constant, M1 times M2 divided by R squared. I think you have seen this formula somewhere. It's a very important formula that talks about finding the size or the magnitude of the force of attraction between any two objects in the universe. Now, the gravitational force that exists between any two objects and the Earth equals what we call the weight of the object. Now, we are introducing yet another term here, or another concept in science, the weight of an object. So we are saying this force here, the gravitational force that exists between an object and that of the Earth, it equals the weight of the object. Now, allow me to call that force Fg, right? So Fg equals the weight of the object. Now, that force of gravity, remember, it is G M1 M2 over R squared. And we are told that this force equals the weight of the object. Now, what is the weight of the object? The weight of the object is found by multiplying the mass of the object by the acceleration due to gravity, ma. So let me put a small g there for ma, or just make it, or you can also say this is mg for the weight. Okay, you can also say that. Now, so the force of gravity, the force of attraction between an object on Earth and the Earth itself is equal to the weight of that object. Now, look at this. If we say M1 and M2, we are actually, I would say, undermining the mass of the Earth, because it's like we're just looking at two sort of relatively equal objects in terms of mass. But we know that an object, the mass of an object compared to the mass of the Earth is very, very small. So what we do is that we can say that this gravitational force that is equal to the weight of the object on Earth is actually this force here. Let's use capital M for the mass of the Earth and the small m for the mass of the object, which could be you or any other object around the Earth, equals that. So this is very important, and I'm going to explain it further when we look at what happens to the object, what kind of acceleration exists on an object that is moving in an up or down motion. Okay, so this is quite important. Let's move on and unpack more of the terms that we're using in projectile motion. Look at this one here. We're now coming to acceleration due to gravity. Okay? Remember now we have spoken about the force of gravity. So, okay, we've got force of gravity. Now we're saying we want to talk about acceleration due to gravity. In other words, we are saying what acceleration is experienced by object due to this force of gravity. Okay. Now, acceleration due to gravity is denoted by a small letter g. So we can use that small letter g to say we're talking acceleration due to gravity. It's a special type of acceleration. All right. Now, acceleration due to gravity is a constant. Now, what is a constant? A constant is something that does not change. Okay? So acceleration due to gravity does not change. It remains the same. So acceleration due to gravity would be the same for all objects moving up or down around the Earth. Okay? So it doesn't matter how big the object is or how small the object is, all those objects moving up and down will experience the same size, the same magnitude of acceleration, and that is the acceleration due to gravity, which is a constant. Okay? Now, it is constant for a specific planet. In this case, we're talking about the Earth. So if objects are moving in an up or down motion on Earth, they will experience the same size, the same magnitude of acceleration. And we are also saying that its value, the value of acceleration due to gravity, does not depend on the mass of the projectile. Remember what a projectile is? Is the object in an up or down motion. So the acceleration due to gravity does not depend on how big the object is, on the mass of the object. So all objects, irrespective of their masses, are going to experience the same amount, the same acceleration due to gravity on that particular planet. If it's on Earth, they will experience the acceleration due to gravity that is for the Earth. And we're going to see now what that is. Okay, now how do we show that this acceleration due to gravity, this g, does not depend on the mass of the object? How do we show that? Now, let's quickly have a look at what we started with earlier on. Remember that we said the force of gravity, okay, or the force of gravity, equals the weight of the object. Okay? Now this is what we know, this is what I said earlier on. Now, if we say that the force of gravity is the same as the weight of the object, remember that the force of gravity is given by that. It is G, capital letter M, for the Earth in this case, if we're looking at planet Earth, small letter m for the object, which I said it could be U, divided by r squared. This should be equal to the weight of the object, and the weight of the object is given by mass times acceleration due to gravity g. Okay, now if we are looking, because here we're looking at one object, okay, it's one and the same object. So we're talking about the same mass, right? So that means m here is the same as the small m here, this m, all right? So this m and that m are the same. So this would mean that if gm, m and divided by r squared equals m times g, m and m can cancel out. So what we have here is g, capital letter M for the mass of the planet, divided by r squared equals g. Now, this tells us that the acceleration due to gravity, which is this, is independent of the mass of the object. It doesn't matter how huge the mass is, how small the mass is, both objects will experience the same amount of acceleration or the same type of acceleration. It will be the same in the sense that it is acceleration due to gravity. It does not depend on how big the mass of objects are. Okay, so that is very important for you to note. We also need to know that acceleration due to gravity is a vector quantity. Now remember, what do we mean by vector quantity? We mean a physical quantity with both magnitude or size and direction. There are two things there. We know how big the quantity is. We also know the direction in which the quantity is moving. Okay, so acceleration due to gravity would always act in a particular direction, and that direction is a downwards direction. And for the Earth, that we should be cautious of. When we are on Earth, everything is accelerated towards the center of the Earth at 9.8 meters per square second. So you would say that the acceleration due to gravity, its direction is always downwards. It acts in a downward direction. Perhaps this explains why things fall down. I mean, if you're a science learner, sometimes you would wonder why is this pen, for example, not falling upwards? I mean, why don't we see it lifted upwards? And every time we throw it upwards, it will definitely come down. And the reason is that whatever is thrown upwards, whatever is moving in air is experiencing an acceleration due to gravity, and its direction is always downwards towards the center of the Earth. Okay, so that, I think, sort of lay some foundation in terms of the vertical projectile motion. And we're going to look at examples. We're going to look at problems and see how we solve them. Let's just continue. Right, let's now talk about graphs of motion involving projectile motion. Now here we looking at how can we sketch the motion of an object if it is moving in an up or down motion. Okay, now let's look at this example here, or this situation here. Suppose an object is thrown vertically upwards, and it is thrown upwards at a certain velocity. We don't know what it is. We are to sketch the following graphs. Let's say, for example, the first one, we are to sketch the displacement versus time graph. You pardon me, I think my vertical axis here is a bit skewed, but it will help us understand what's happening here. Look, we are told that the object is thrown vertically upwards. So if this is our displacement axis, so this will be delta y, okay, the displacement axis. It is displacement versus time, therefore this axis here will be time, delta t, okay, time. Another thing we need to put in here are the units in which these quantities are measured in. We know that displacement is measured in meters, time is measured in seconds. So we can do that. We are told that this object is thrown upwards at a certain velocity, okay? And then it's going to come back after some time when it is thrown up. So we will take the initial position of the object as the 0 position. So it hasn't moved any displacement, doesn't experience any change in displacement. And after some time, it is gonna move up, and what we know about anything thrown upwards, it's gonna move up. So after some time, say at that point, after that time, it's gonna reach a maximum height where it's gonna stop momentarily, just for a very short time. Okay, it stops there, and it will start to move in a reverse direction. In other words, coming downwards this time. And after some time, it will then reach the point at which it was projected. Okay, so say it is that point there. So this will mean that the graph for displacement versus time will be a curve like that. Okay, so this object moved upwards, had some change in the displacement or in the vertical height, the vertical displacement, which is delta y, up to some point there. Then, after stopping momentarily there, it comes down to where it was thrown from. Another thing you should look at here is that the time it took to move from 0, let's call it T1, to move from 0 position to the highest or maximum position, the maximum height, it's the same, or it will be equal to the time it takes to fall from that maximum height back to where it was thrown. Let's call it T2. So in this situation, what we have also learned is that T1 will be equal to T2. Now, how do we know that? We can see that if we were to draw a line of symmetry here that divides the graph into 2 equal parts, you will see that this part here sort of, in fact, equals that part there. So the 2 parts are equal, and therefore the time it took for the object to move up and reaching its maximum height equals the time it took the object to move from its maximum height back to the position where it was thrown. Okay, so T1 equals T2 in that case. This is also very important because you will need this to answer some of the questions in the problems we're going to look at and also in your exams. Okay, let's come to the next one. Say now we had to sketch a velocity time graph. Now, once again, we know that time is always on the x-axis. So the time is there, measured in seconds. This time we're talking about velocity versus time. So v, and in what units is v measured? Meters per second. Okay, so we can put that there. We are to draw a graph of velocity versus time there. Now, there is something very important I need to explain here. Okay, if this line there is the time axis, I want to put it somewhere in the middle there so that I can be able to explain clearly what I want to say to you here. So let's have our time axis at that point. So the time in seconds, let it be there. Now we are told that this object is thrown upwards at some velocity. So somebody throws the object upwards at some velocity. Now this means that we can't say that this 0 point here, that is where the velocity was when the object was thrown. Definitely the object was thrown at some velocity, so we will assume that that velocity is somewhere up there. So let's take the upward, for example. Let's take the upward motion to be positive. If we take this upward motion to be positive, the velocity at which the object is thrown out upwards could be somewhere at that point. Why? Because this part is the positive part of our y-axis, and this is the negative part of our y-axis. But this time we're talking the velocity axis. So if it is thrown upwards at that velocity, what we know is that it is going upwards, and as it moves upwards, okay, its velocity decreases until it reaches a zero velocity. And from that point, it begins to come back towards the point where it was projected upwards, and its velocity is increasing and increasing and increasing, so it hits my hand with a certain velocity. Now, this means that there is a time when the velocity of the object was at zero. So we have some point there, okay? This is at t1 when the velocity of the object was zero. This is at the maximum height where it stopped a little bit and then began to fall downwards, okay? And as it comes downwards, its velocity is actually increasing, and it hits my hand with some velocity. So say it hit my hand with a velocity maybe at that point. So that means that when the time it's somewhere there, it had a velocity of minus. Now that is what I also want you to notice. Minus velocity. Why minus? Because we have said, let's take the going upwards as positive. So the coming downwards, remember velocity is a vector quantity. It's negative. And hence the value of velocity here is taking a negative sign. That is just to tell us that it is in the opposite direction. So the velocity decreases to zero and start increasing in the negative direction. In other words, downwards this time to some value there. And that is the value at which it is going to hit my hand in this example with. All right. So that will be the velocity time graph for a projectile. Okay, something thrown upwards and coming downwards. All right. Now, let's move on and come to the last graph that I want us to draw. And this graph is a graph of acceleration versus time. Now, can you guess what is going to happen here? I wish you could. And I think you can, actually, because we know that acceleration due to gravity is constant. And what does it mean? It is not changing over time, okay? So if we have our acceleration due to gravity here, this is acceleration due to gravity measured in meters per second. This is the time axis measured in seconds, right? Pardon me, acceleration due to gravity measured in meters per square second, not meters per second. Now, this is the time axis. We have just said that acceleration due to gravity, G is constant, not changing, okay? And we know it to be equal to 9.8 meters per square second. That is the value of acceleration due to gravity. So it doesn't matter the change of time, but what we know that is that the acceleration due to gravity is not changing. So if it is there, so if at that point there, if that point is our 9.8 point, the graph of acceleration versus time, this line shouldn't be slanting like that. So acceleration due to gravity will remain a constant throughout the motion. It is 9.8 meters per second. So at time 1, okay, at t1, it's 9.8 meters per second. At t2, it's still 9.8 meters per second. At t3, still 9.8 meters per second. T4, still at 9.8 meters per second because it is a constant, it does not change. So that is, or those, if you like, are the graphs of motion basically that we need to know when we looking at vertical projectile motion. Okay, think you have understood that quite well. You are going to apply this in solving problems. So it is very important to understand it so that when a problem is posed to you, whether it is in the form of graph or perhaps in form of equations, as I'm going to show you, you will be able to answer it or solve it. Let's move on. Now let's look at example 1. Example 1 talks about an object being thrown upwards with a velocity of 24.5 meters per second, and it takes 5 seconds to come back to the thrower's hand. So the thrower's hand obviously becomes our reference point. Now, because here we're talking about objects being thrown up and down, and we're talking vector quantities like velocity, we'll then have to define our directions. Okay, so I want us to take upwards. Okay, upwards is positive, so it means that downwards will be negative. Okay, now this object is going upwards at this velocity. Upwards is positive, so our V initial will be positive 24.5 meters per second. Okay, what else is given to us? We also have time, the total time it takes to go up and back to the thrower's hand. Time is not a vector quantity, so we don't worry about the plus and minuses. It's a scalar quantity, and time is 5 seconds. Okay, that's what is given to us. Another thing that is given to us, but is not written on this question here, but as long as we know that this is an up and down motion, it's a projectile motion, we know that all objects that are in a projectile, moving up and down, are experiencing some acceleration, and that acceleration is a constant acceleration due to gravity G, and it's always acting downwards. And what is downward? Downwards is minus, so it's going to be minus 9.8 meters per square second. Okay? Now, the first question that we have here is that from this information, can we sketch a displacement time graph? Now, we need to know, we know that when something is thrown upwards, it's going to go up. Okay, it's going to go up and then reaches a point and comes back, okay, in the same path, okay, that way. So the displacement or the position time graph that we're going to have is such that you have got some position, change in position going up, and then you have got change in position coming down, and then back to the 0 point of your displacement or your change in position. Now, can we know how far the object moved from the moment it was thrown up to the moment it reached its maximum height and turned back? Okay? Of course we can, and we can use the equation that says V final squared equals V initial squared plus 2a, and in this case we can be specific. It's acceleration due to gravity G delta x. Okay, and if you work this out, you know your initial velocity, your final velocity here, it's going to be 0 meters per second at that point. So we know that this will be 0 squared equals. What is the initial velocity? Initial velocity is what is given to us there, 24.5 meters per second squared there, plus 2 into our g is minus, and therefore this will be minus 9.8 meters per square second times delta x. Now delta x is what we're looking for. Now this, if you work it out, it will be 6. In fact, you square that and take it to the other side, it's going to be minus 600.25 equals, this is going to give you minus 19.6 delta x. And if you work out delta x, okay, if you work out delta x then becomes 30.63 meters, because that's displacement. So we know how far it has gone upwards before it turned down, so we can have a sketch graph now of displacement versus time. Now, how are we going to draw that? It means we'll have axis here, okay? That will be your displacement axis, or change in position, and this side will have our time axis. Right, now, so this is displacement. Let me call it delta y, and I think it will be more appropriate to call it delta y because we're talking vertical displacement. So perhaps even here, when we have calculated here, this delta x here, we remember when you're talking vertical, you can make it y, because your y is your vertical displacement. So that will be delta y. So that is in meters. We know it was thrown upwards, and its displacement was 0 at the beginning. So that's the 0 point. This is your time in seconds. It went up half the time. Remember, it went up for 5 seconds, so half that 5 seconds is the time it took to get to the top. So from 0, let's say that point there, it's your half the time, which will be 2.5 seconds. So let's say that is your 2.5 seconds, and that then becomes your 5 seconds. And remember, this is your time axis in seconds. Now, if your 30.63 mark is there, so this is 30.63, okay? Where these 2 points meet, that is where the object turned. That's the turning point. And when it came back, it reached the thrower's hand after 5 seconds. So your graph, your displacement time graph is that. It's a parabolic shape that you're going to have. Remember that if I was drawing this to scale and everything was neat, I would have a nice curve there, and the turning point will be right at the apex of that graph there. So that is how your graph will look like, displacement time graph. Okay, coming down to the next one, number B, velocity time graph. Okay, velocity time graph here. Let's again have the axis. Okay, so there is our vertical axis, which will be V in this case, and here is our horizontal axis, which will always be the time axis when we draw the motion graphs. So this one will always be time measured in seconds. This one is velocity measured in meters per second. Okay, and now there's something that I did here. In terms of the space that I have, I may not be able to draw the graph that I have to do. So what I need to do is to come back to this line here, okay, and then change it, okay. So I need to change this line here, okay, because I've got some negative velocity at the end. So I would need to have my line coming from somewhere in the middle here. I would need the negative part of my vertical axis, which is my which is my time axis. I mean my velocity axis. So there is the time axis. Okay. T in seconds, V in meters per second. Okay. And then now this object is thrown upwards at some velocity, and that velocity is 24,5. So 24,5 there. It is positive because upwards was positive, okay? And when it begins to come downwards, it will be negative. Now, if it was thrown up at 24,5 meters per second upwards, it's gonna reach the thrower's hand after 5 seconds at a velocity of minus 24,5 meters per second. And that is when the 5 seconds mark is reached, okay? Now, half the time, remember the 2.5 seconds that I spoke about up there? At that half the time, that is the turning point of the object. And at that turning point, the object is at 0 meters per second. In other words, it is not moving. So if that is 2.5, that is where the object has got 0 meters per second as its velocity. So this will be 2.5 seconds. All right. Now, the points here, if you like, if you were to plot them, there is one, the minus 24.5 meters per second when the time is 5 seconds, and then 0 meters per second when the time is 2.5, and your initial velocity of 24,5 meters per second at the beginning. Now, if you join these 3 points here, you would have a straight line in that direction or a graph of that sort. And if you look at that graph, if you're familiar with straight line graphs, you'll see that this graph has got a negative gradient. Okay? It has got a negative gradient. Okay. Now, negative gradient, in this case, what is the gradient that we're getting here? If you work out the gradient of this graph here, you would see to get the gradient, you would know generally from mathematics, you know, gradient is change in y over change in x. Now, what do you have in your y? Change in v over change in time. And what is this thing called change in v over change in time? That is your acceleration. And in this case, it's a special type of acceleration, which is acceleration due to gravity g. And if you calculate for it, you get it to be negative. And I think that confirms why we took our g to be minus 9.8 meters per second there. It tells you that this graph, in fact, the graph is confirming the fact that g has to be negative there. Now, the last one, acceleration versus time. You would see if we calculated that we get the minus there. So it was going to be minus 9.8 meters per second as we know it. I mean, per square second as we know it. And then how do we draw that graph here? Now, again, to draw graphs, we need axes. We need the vertical axis. We also need the horizontal axis. But I need to be careful again here because my acceleration is negative, so it has to be in the negative section of my vertical axis. So I'm going to put my time axis somewhere there. Okay. Right, I think that one is not so neat. Let me have that one. Okay. Now, the acceleration is on the vertical axis. It's measured in meters per square second. My time is on a horizontal axis. It is measured in seconds. Please make sure that when you put your quantities on the vertical and horizontal axis, put the units in which they are measured as well. That gives you marks in the exam. Now, the acceleration is minus 9.8 meters per square second. So my graph for the acceleration is that one. And that tells you that the acceleration is constant. Okay? So that means it does not change. And we know it, that acceleration due to gravity stays the same. Okay? And of course for Earth, for planet Earth, it's 9.8. For any other planet, it will be something else, but it will stay constant for that particular planet. All right. Now, how do equations of motion apply to vertical projectile motion? As we know that the equations of motion we worked on when we were doing revision of grade 11 work applied on horizontal motion. It applied on what we call rectilinear motion. But then, can we use the same equations for this type of motion? The answer is yes, we can. Okay, we can use the same type of equations. All right, but then what is the difference? Equations of motion are used to solve problems in projectile motion. All right? Okay, so what are those equations if we were to go back and revise a bit? We know, one, that V final equals V initial plus acceleration times change in time. Okay, so that is the first basic equation that we can look at. The second one that we know is that delta y, and I'm basically saying delta y this time because we're talking vertical, so it won't be delta x. So delta y equals V initial delta t plus half acceleration, and of course acceleration due to gravity, times delta t squared. 3, we also have this one that says V final squared equals V initial squared plus 2a delta y. Okay, and I'm using delta y again, not delta x, because we're talking vertical motion. And the fourth one, which is not as usually used but very important, is this one. Delta y will be equal to, in brackets, V final plus V initial divided by 2. So this is average velocity times delta t, change in time. So all these are the equations that will be applicable in solving problems in our vertical projectile motion. Okay, now change in displacement, you would notice that we're talking delta y. Why? Because that change in displacement is along the vertical, right? Okay, now it's time for us to look at some example to see how we can use these equations to solve problems. Okay, let's look at example 2. A boy standing on a building. So he's right up in a building. He throws a ball vertically upwards from a position 3.5 meters above the ground with an initial velocity of 10 meters per second. So that should be meters per second up there. Ignore the effects of air resistance and answer the following questions. Okay. Now, what is the magnitude and direction of the acceleration of the ball? A very easy one to answer. What is that? The acceleration is, what is the magnitude? The magnitude is 9.8 meters per square second. And what is the direction? Downwards. Okay? This we know is constant and it remains like that. So we don't have problems answering that type of equation. Right, the question is calculate the maximum height reached by the ball above the ground. Now, it talks height, so I need to pick on an equation that talks delta y. Okay? And what do I know about what has happened to the object? Okay, I know that the object is projected upwards at some velocity. Okay, so that becomes the initial velocity. Okay, that would be equal to, maybe let's write it down from where the question is. We are told in the question that it is thrown upwards at 10 meters per second. Okay, and the initial position of the boy is 3.5 meters above the ground. Okay, so if the initial velocity is 10 meters per second, what is going to be the final velocity? We know that if something is thrown upwards, it goes up at the maximum height, its velocity is 0. So final velocity is 0 meters per second. We also know, although they haven't told us, that acceleration is 9.8 meters per square second because this is a projectile motion. Okay, so for me to calculate the maximum height reached by the ball, remember maximum height above the ground, I must know how far it moved when it was thrown. Okay, so to do that, I need to use this equation. V final squared equals V initial squared plus 2 times the acceleration delta y. So I will be able to get what delta y is. Why? Because V final I know it's 0. So I'll say this is 0 squared equals V initial. Now, very important. We're dealing with vector quantities here. So we need to make a choice. Let's take the upward motion to be negative. So if the upward motion is negative, the velocity with which the ball is thrown upwards is going to be negative 10. So this will be negative 10 squared. I need to show that I'm taking upwards as negative. So that will be negative 10 all squared. Plus 2. Acceleration is going downwards. So because acceleration is going downwards, downwards is positive. So this will be 2 times positive 9.8 meters per second. Per second squared times change in vertical displacement. So this is going to be 0 equals, we know this is going to be 100 plus, what will this be? 2 times 9.8 is going to be 19.6. Okay, 19.6 delta y. Right. Therefore, delta y would be equal to, we're taking 100 to this side, so it must change the sign, is now minus 100, divided by positive 19.6. Sorry, 19.6, this one here. And that should give us, let's work it out here. This is now 100 divided by 19.6. And the answer is 5.10, so 5.1 meters. Now, this is the height that the ball reached from the point where it was thrown. So if you like, we've got this situation here. We've got this 3.5 meters. That is the height from the ground to the building. Then the boy throws this object from here, and the object goes like that. So from here to there, we have calculated it is 5.1 meters. Now, this is the ground. That's the maximum height reached. The question wants us to find out what is this maximum height. Okay? This maximum height here. That is what the question wants us to do. So this delta y here. Okay, so if this part from there to there is 5.1 meters, from here to there is 3.1 meters, the maximum height will definitely be the sum of that. But another thing that you need to realize from our calculation here is that this is going to be minus 5.1 meters. Why minus? Because displacement is a vector quantity. Going upwards is minus. Coming downwards is positive. So this time, the object was still going upwards. From there to there, it's still going upwards. So that becomes minus. But that is only for direction. If I want the total displacement here, I just have to add the two, the total height. So maximum height reached. Maximum height then equals 3.5 meters plus the 5.1 meters. And that gives us 8.6 meters. So that is how high the object moved above the ground. Okay, that's the maximum height reached. Right, let's move on. The next question says, what was the velocity of the object at its maximum height? Whew, a nice one. We know that at the maximum height, it's where it tends. That is the point. Where it tends there, v equals 0 meters per second. So velocity equals 0 meters per second. What did I do here? So velocity equals 0 meters per second. Okay. So that's what the velocity is at the maximum height. Now, in the previous question, we were calculating the time it took the object to go up to the turning point, coming back to the thrower's hand. And so we were looking at that time only. But this time we want to remember the person is throwing this up and down from 3.5 meters above the ground. So we want now to find out how long did it take, okay, for this projectile to go up to the maximum point, coming back and hitting the ground now. So that's what we want to do. But then we need to take certain things into consideration here. We need to know that initially we had this 3.5 meters. Something is thrown from that point, okay, upwards, right? And we calculated for that distance for this thing to be thrown upwards, reaching a maximum height, coming back, and it hits the ground there. Now, this one here, that height there is found to be 5.1 meters. So in total, this height here is 8.6 meters. Okay, so that is what we have here. That's what we have. And if we regard this, the return trip, okay, if we look at the return trip of the ball from the top to the bottom, if we just look at that, we can say, okay, let's take the downwards to be positive because we're looking at one particular trip here. So if we take the downwards to be positive, it would mean that our G is now plus, because G is always downwards, I think you know that. This is plus, so G is positive 9.8 meters per square second this time. And we also know that at the turning point here, the velocity of the ball is 0 meters per second. Okay? And therefore, what are we calculating for? The question wants us to get the total time taken by the ball. Now, if we know the time it took to move from the top to hit the ground, then that time added to the other time we had is going to give us, in fact, added to the time that it took to move from this point, the 3.5 meter mark, to the top, if we have that time, plus this time here, we'll have the total time. So what do we need to do? We need to get the time it takes to move from the top to hit the ground. And what equation can we use there? Okay, with this information. Remember, another thing that is given to us now is this height here, delta y, I will call it delta y. It's 8,6 meters. And we'll take it to be positive as well because it is, the object is moving downwards. Okay, so what equation are we going to use? We would use this equation here. Allow me to use the space this side here, down here. Right? Let's use this equation here, delta y equals v initial delta t plus half g delta t squared. Okay? And what is our delta y? Delta y is 8.6 equals initial velocity. The initial velocity at the top there, we know it was 0. So 0 times delta t, we know that is going to be 0, plus half, what is g? G is 9.8. Okay, let me just put it in brackets, delta t squared. So what are we having at the end? At the end, we're having this, we're having half 9.8, half 9.8 is 4.9. So 4.9 delta t squared equals 8.6. Therefore, delta t equals the square root of. Now, let's find out what is 8.6 divided by 4.9. Okay? 8.6 divided by 4.9. That's 1,76. So it's a square root of 1,76. And what is the square root of 1,76? Okay, let's just go straight, say square root of the answer. Let's see what that is. It tells us the time is 1,32 seconds. So 1,32 seconds. Now, this is not the answer. This is only the time it takes the ball to move from that position to hit the ground. Okay, that is the time. But then the question says calculate the total time taken by the ball. So the total time taken by the ball will be this time here plus this time there. Okay, and then we have this time here from our previous calculations. And then how do we get that? Now let's work it out. We know previously that the time to move from here to there, we found it to be 1,02 seconds. So this is 1,02 seconds. So we'll say that the total time then equals what we got first, 1,02 seconds plus what we're having now. What is the time now? Found it to be 1,32 seconds. And what is that? That gives us 2,34 seconds. Okay, so that is the total time. Right, so we've answered that question. Now moving on to the next one, it says calculate the velocity with which the ball hits the ground. Now the velocity with which the ball hits the ground, we can use this equation here, V final equals V initial plus G delta T. Okay, now V final is what we're looking for. So it will be V final equals, V initial is the ball's velocity at the top, at the turning point, we know that it's 0, plus this is what? Positive 9.8. And what is our time? The time to come from the top and hit the ground. This is the time. Okay? That's 1,32 seconds. So 1,32. And what are we getting from there? You can quickly use your calculator, 9.8 times 1,32 seconds. And it tells us that is going to be 12,936. Okay? So that is 12,936. So 12,936 will be 12,94 meters per second. Okay. Now, coming down to the next one, it says here, draw a rough sketch of the velocity time graph showing relevant points on your velocity time graph, time axis. Okay. Now, let's see how we can do that. Let me get some more space here. Okay, so I have enough space now. It's a velocity time graph. I do have some negative velocity, remember, because now we are looking at the whole journey. We're looking at the ball going up and coming down and hitting the ground there. So there's the ball, it goes up, comes down, hits the ground there. Okay? Now, because I'm looking at the whole picture, going back to the initial situation where we took upwards as positive. So anything going down will be negative. In other words, what I'm trying to say is that I know this is the velocity with which this is the velocity with which the ball hit the ground. So because this velocity was downwards, it is going to be negative in my drawing. Okay. Now, let's have the axis. Let's have the axis. Let me have my vertical axis there. And let me have my horizontal axis. I think here I need to have it starting from somewhere there. Okay. Right. And now, labeling them, this is V in meters per second. Meters per second. This is T in seconds. All right? Now, the times that I have, this object is thrown upwards at a velocity, okay? Right? And the velocity is, it's actually thrown out upwards at 10 meters per second, there. I have also calculated that after 1,02 seconds, so if this is 1, that is, let me do it this way. If this is 1, that is 2, and that is 3. Okay? 2, 1. At 1,02, somewhere very close to where 1 is, that is where the object, the ball is making its turn right up at the maximum height reached. So the velocity is 0, so the point is there. At the time, okay, remember this time here, this total time here, at 2,34 seconds, 2,34 seconds will be somewhere there. At 3,24 seconds, this object, the ball,
is hitting the ground with a velocity. And that velocity, we have calculated for it. We found it to be what? 12,94 meters per second. And it is negative because it's now downwards. So I'll say minus 12,94 meters per second. So at this point there, the ball is hitting the ground, okay? I'm trying to make it so that I have my straight line here. Okay, so here I would have a straight line if I join those points there like that, and this will be my velocity time graph, and as you can see, it's a graph with a negative slope. Okay, I have explained what a negative gradient or negative slope is all about, and in this case it's a specific gradient, is g, which is minus 9.8 meters per second in this case. Okay, all right, and that is how you should draw your graphs.
That brings us to the end of the lesson for today. I hope you enjoyed it. My name is Tinigo Kosa, and I'm signing off. Good luck with all your science activities.